Okay, let's assume this is a wire, right? So I'm going to put a current on this direction. This is I, a current. So the current will flow around this. You know, when a current is moving this direction, right? This direction, there will be a magnetic field. The magnetic field will be over here. But when it comes to the these corners, right? These corners, the magnetic field will be bent like this. Okay, this happens. So I have put a current to go on this direction, but you know, the electron's direction is completely opposite from the current direction. So in here, the electrons are moving opposite direction, right? Electrons are moving opposite direction. So now let's move this theory to this benzene molecule, right? In NMR, we are applying a magnetic field. Let's take as B naught. It's upwards. So what happens here is, you know, in benzene there are 5 electrons, right? There are 5 electrons, and electrons will circle like this. Electrons will circle, it will rotate like this. So due to this rotation, you know, these are electrons which are moving. So current is going the other direction. Magnetic field will be applied over this direction. But when it comes to the corners, these magnetic fields will bend like this. Just the thing over here, just the theorem over here. Right? So these are magnetic fields. So now let's see these hydrogens here. These hydrogens, you can see this hydrogen will affect by 2 magnetic fields, right? One is the applied magnetic field, which is B naught, and the other one is magnetic field due to this electron's rotation, right? It is also in the same direction as the provided magnetic field. So we will add the second magnetic field. This is the total magnetic field which will be affected the hydrogen to our NMR spectroscopy, right? So B if. So you know, this will be affected higher, right? This effect is higher. BF is higher than the usual one because this added value. So the frequency, you know, frequency of our NMR is directly proportional to the magnetic field which is sensitive by the each hydrogen atom. So frequency will be higher. So normally in benzene, it will give the signal around 7.2 ppm, right? 7.2 ppm. Why is this? This is greater than the normal CH2 bonds, CH3 bonds. It's because of this effect, right? It's because of this effect. This effect will add some additional magnetic field to our original hydrogen atom, which will increase the frequency, right? We will take another example here. Look at this example. This is aniline, right? You can see this is also having likewise this a ring like structure. So the same phenomena is happening over here too. Now you have to visualize this in 3D aspects, right? You know, the electrons will move these directions. So the magnetic field will be just like the before. So they will circulate like this. So you can see in these inner hydrogens, the magnetic field due to the electron rotation will be opposite relative to the applied magnetic field, but the outer hydrogens will have the same direction of the applied magnetic field. So these outer hydrogens will have the total magnetic field as B0 plus Bi. Bi is the magnetic field due to the rotation of the electrons, but the inner hydrogens, they will have the magnetic fields towards the down, but our applied magnetic field is upwards. So in inner hydrogens, total magnetic field will be given by B0 minus Bi. This is basically a huge variance, because usually this will give minus 2 ppm, which is this one is normally giving a 7.2 ppm. It can be vary, but it's around this value. You can see a huge difference between those two. It is because this effect, right? It's because of this effect. So I hope you have an idea about this topic.